There are roughly 600 blast furnaces left in the world, and almost every one of them is on fire right now. Not warm, not idling, on fire, at about 1500 degrees Celsius, the way it was yesterday and the way it will be tomorrow. One of them, on the Rhine at Duisburg, was lit and then burned without interruption for 21 years before anyone put it out. 21 years. No nights off, no weekends, no maintenance Sundays. And the reason is not that nobody thought to try. It is that switching it off is the single most expensive thing anyone at that plant could possibly do. We are used to the idea that a factory closes, the shift ends, the lights go down, the cool, and in the morning somebody starts them again. Almost every industrial process on Earth works that way. A blast furnace does not. From the day it is lit to the day it is deliberately killed, it runs continuously, and the period between those 2 days has a name that tells you everything about the scale involved. It is not called a shift or a season, it is called a campaign. Modern campaigns are to last 15 to 20 years, and the best-run furnaces in the world push past 20, and here is where the ordinary logic breaks. You would expect that a machine this large, this hot, and this expensive to feed would be shut down whenever demand dropped the way a car engine is shut off at a traffic light. The opposite is true. Stopping a blast furnace does not save money. Done badly, it destroys the furnace, and a replacement lining costs more than 200 million euros and takes months to install. Done well, it still shortens the life of the thing you were trying to protect. Frequent stops reduce campaign life. The furnace is not damaged by being run hot for 20 years. It is damaged by being allowed to cool. So the question this video answers is not how a blast furnace works, it is why it refuses to stop and what exactly happens in the hours after the heat begins to leave. Because the failure has 3 stages, and they are known, named, and classified by the engineers who recover them. Stage 1. The connection between the taffole and the turris is lost, but there is still heat in the hearth. At stage 2, the molten iron itself begins to solidify. Stage 3, everything liquid in the hearth is frozen solid, and what you have is no longer a furnace. It is a building with several hundred tons of iron set inside it like concrete. 3 stages. Everything in this video exists to stop the furnace from taking the first step. Before we climb the cast house stairs, subscribe, because this channel takes apart the machines you pass every week without ever seeing inside them. And now let us look at what is actually in there, because it is not what most people picture. The first thing to understand is that a blast furnace is not a furnace. The name is a historical accident, and it misleads almost everyone. A furnace, in the ordinary sense, is a box you put something into and heat from the outside. There is a burner, a flame, a chamber, and a thing being cooked. A blast furnace has none of that. There is no flame applied to anything. Nothing is heated from outside at all. What it actually is a countercurrent chemical reactor, about 30 meters tall, and the reaction happens inside a moving column of solid material that is also the fuel, also the structure, and also the thing being processed. From the top, in continuous layers, come iron ore pellets, limestone, and coke. Coke is coal that has been baked until the volatile material is driven off, leaving a hard, gray, porous carbon that looks like petrified sponge. Those layers descend slowly, over 6 to 8 hours. From the bottom, through a ring of nozzles called tires, comes air. Not cold air. Air preheated to around 1200 degrees Celsius, driven in hard, which is the blast the name refers to. The hot blast, it's the coke at the bottom and burns it. That combustion is the only heat source in the entire machine, and it happens inside the material, not against it. The gas produced by that combustion rises up through the descending column, and as it rises, it does 2 things simultaneously. It heats the material coming down, and it strips oxygen out of the iron ore chemically, using carbon monoxide, which is what actually turns rock into metal. By the time a pellet has traveled from the top of the stack to the bottom, it has been heated, reduced, and melted, and it arrives in the hearth as liquid iron at about 1500 degrees, with liquid slag floating on top of it. And that liquid has to come out several times a day through a hole, not a valve, not a tap, in any mechanical sense, a hole in the side of the hearth that is drilled open and then plugged again. The tap hole is opened with a long drill that bores through a plug of hardened clay. And when it breaks through, liquid iron comes out in a stream that lights up the whole cast house. It runs down refractory line channels called runners which split the flow, sending the slag one way and the iron another because the slag floats and can be skimmed off at a dam. The iron goes into ladle cars, insulated vessels on rails, shaped like torpedoes, which carry it to the steel-making shop while it is still molten. Then the taphole is closed again with a machine called a mud gun, which fires fresh clay into opening under pressure, and the clay bakes hard in place until the next cast. That cycle repeats around the clock. The taphole is opened and resealed thousands of times across a campaign, and it is the most heavily worked single point on the entire vessel. Everything else about this machine is continuous. The taphole is the one place where the process is interrupted deliberately several times every day at exactly the point where the wall is holding back hundreds of tons of liquid metal. Now hold on to one detail, because everything later depends on it. Coke is not just the fuel. Coke is also the skeleton. The reason gas can pass upward through thousands of tons of ore at all is that the coke layers stay solid and porous while everything around them softens and melts. The coke holds the column open. It is load-bearing. It is the only thing in there that does not turn to liquid, and it is simultaneously the fuel being consumed, the reducing agent doing the chemistry, and the structural lattice keeping the gas path clear. Take away the coke and you do not have a cooler furnace. You have a blocked one, which means the process cannot be turned down the way you turn down a stove. There is no dial. The only way to reduce the heat is to reduce the blast, and reducing the blast slows the combustion, and slowing the combustion cools the column, and a cooling column stops flowing properly. Everything in a blast furnace is coupled to everything else, and the coupling only works in one direction, fast and moving, which brings us to the part that reverses what most people assume about a machine like this. Ask anyone what the enemy of a blast furnace is, and they will say heat. It seems obvious. 1,500 degrees inside a steel shell for 20 years with molten iron sitting in the bottom. Surely the heat is what wears it out. It is not. The refractory lining that stands between the liquid iron and the steel shell is designed for that temperature. It sits at that temperature for 2 decades and survives. What destroys it is the difference between one temperature and another, thermal cycling. Every time the furnace is allowed to cool and is then brought back up, the lining expands and contracts unevenly, brick against brick, and cracks open along the joints. The heat is the working condition. The change is the damage. This is why the industry measures a furnace in campaigns rather than in operating hours, and why the record holders are always the furnaces with the interruptions. It is a documented relationship, not a rule of thumb. Frequent stoppages reduce campaign life, and the loss of output is worse than the downtime alone would suggest, because each stop and start cycle takes something permanent out of the lining. A furnace that ran hard and uninterrupted for 20 years can be in better condition than one that ran at half the output with a dozen stops in the same period. It helps to know what the end of a actually costs, because that number is what every operating decision is measured against. A Forey line is a construction project. The furnace is taken cold, opened up, and the entire inside is demolished and rebuilt. Published figures for recent projects sit in the range of €200 million to $400 million for the work itself. ThyssenKrupp's Svelgen rebuild, POS, Cisco's program across 2 furnaces, U.S. Steel's planned reline at Gary Works. On top of that, the furnace produces nothing for somewhere between 1 and 3 months, and for a large furnace, the lost output alone runs into tens of millions more. So a plant is not choosing between running cost and standing cost. It is choosing between burning coke today and bringing forward a 9-figure rebuild by a year or 2. Every avoidable stop moves that date closer, and the date is not on a maintenance calendar. It is set by how much refractory is left in one place. Nobody can measure directly. And there is a second layer to the inversion, which is where it stops being counterintuitive and starts being genuinely strange. The furnace does not merely tolerate its own heat, it uses that heat to build its own armor as the burden descends and the slag becomes liquid. Some of that slag freezes against the cooled inner wall and stays there, forming a solid crust called the skull. The skull is not designed in. It grows out of the process itself, and it is what the liquid iron actually touches for most of the campaign. Operators deliberately encourage it, sometimes by adding titanium-bearing material to the charge, which forms a tougher protective layer on the half, where erosion is worst. So the lining is protected by a coating made of the process, and that coating exists only because the furnace is running. Cool it down, and the skull cracks and falls away. When the furnace comes back up, the liquid iron is touching bare refractory again, and the erosion clock that governs the entire campaign starts running faster. The people who operate these things are not keeping the furnace hot because it is convenient. They are keeping it hot because the hot state is the protected state, and every hour of cold is an hour with the armor off. The next question is what that armor is actually protecting, and the answer is a structure with almost no moving parts at all. Strip away the pipework, and a blast furnace is a steel shell shaped like two cones joined at the waist, and every part of that shape is doing a specific job. The upper section, the stack, tapers outward, going down, because the burden expands as it heats, and the widening profile keeps it from jamming. The waist is where the ore softens. Below that, the Bosch tapers inward toward the tool layers, concentrating the hottest zone. And at the bottom sits the hearth, a thick cylindrical basin that holds the liquid iron and slag until they are tapped out. Inside the shell is the refractory lining, and in a modern furnace that is thousands of tons of it. When ThyssenKrupp relined the Svelgen No. 2 furnace after its 21-year campaign, the job took over €200 million, 7,100 tons of refractory material, and 2,300 copper cooling plates. Those numbers are worth sitting with because they are the price of the lining alone on one furnace once. The copper cooling plates and staves are the part almost nobody outside the industry knows about, and they are the reason the shell survives at all. They are hollow. Water is pumped through them continuously, and they sit between the refractory and the steel shell, pulling heat out of the wall. Without them, the shell would reach a temperature at which steel loses its strength, and a shell that loses its strength under the weight of thousands of burden does not bend gracefully. It fails. So the staves are cooling elements. That is what they are for. But here is the part that only makes sense once you know about the skull. The staves are also the reason the skull exists. The skull forms because the inner wall is being held cool enough for liquid slag to freeze against it. Remove the cooling and you lose the protective crust as well as the shell. The cooling circuit is simultaneously the thing that keeps the steel from softening and the thing that grows the armor on the other side of it. One system, two functions, and both of them stop working the moment the water stops or the furnace goes cold. There is one more set of components worth naming because they are the only parts of a blast furnace that are treated as disposable. The tuyères. The nozzles that inject the hot blasts through the wall into the hottest zone of the machine are water-cooled copper, and they sit directly in the combustion zone. They do not last a campaign. They last somewhere between 6 and 18 months, and then they are changed, one at a time, on a large furnace that has 20 or more of them. A tuyère change is a short-off blast, done as routine work, and the furnace barely notices it. That distinction matters for everything that follows. There are parts of this machine you can replace while it lives, and parts you cannot. And the boundary between the two categories is not about how expensive they are. It is about how deep inside they sit. A tuyère is in the wall so you can reach it. The hearth bottom is under several hundred tons of liquid iron, so you cannot at any price until the campaign is over. And now the vulnerability because it is not the fire. Water and molten iron must never meet. A cooling circuit runs through the wall of a vessel holding several hundred tons of liquid metal under pressure for 20 years, and the entire monitoring regime of a modern blast furnace exists mostly because of that one sentence. What happens when a leak starts and how anyone finds it is where this gets genuinely uncomfortable. Here's the problem that defines blast furnace operation, and it has nothing to do with fire. You cannot look inside, not with a camera, not with a borescope, not by opening a hatch and shining a light. The interior is a 1,500-degree column of moving solids and liquids, and it stays that way for 20 years. Direct inspection is not difficult. It is physically impossible, which means the condition of the most expensive part of the machine, the hearth refractory, the part that determines when the campaign ends, has to be inferred entirely from the outside. Modern furnaces are instrumented accordingly. A large furnace carries something in the order of 200 distinct thermal zones, 30 or more separate cooling circuits, 20 or more tuyères, and thousands of individual measurement points feeding into the control room. Operators are reading temperatures through the wall and reconstructing what the inside must look like, the way a doctor reads a patient without opening them up. And the thing they are watching for most closely is water. A cooling stave that develops a small internal blockage does not announce itself. Monitoring specialists describe the sequence in stages. A partial blockage of a few millimeters reduces flow in one gallery. The wall behind it loses its heat sink, and within a matter of days that shows up on the shell as a hotspot tens of millimeters across. Over the following 2 weeks, the hotspot works into the refractory brick behind it. Somewhere around 3 weeks from the first restriction, the furnace has to come off blast whether anyone planned for it or not. 3 weeks from a blockage you could cover with a fingernail to a forced shutdown of a facility that produces thousands of tons of iron a day, and the reason it matters so much is that a hotspot is the beginning of a path toward the one event nobody wants: cooling water reaching the hearth. Water meeting molten iron flashes to steam instantly, expanding roughly 1,600 times inside a closed vessel. That is why the water temperatures and flow rates on those circuits are lobbed continuously, and why a small change in a differential reading is treated as urgent rather than noted for the weekly report. There is one more constraint on all of this, and it is brutal in its simplicity. Most parts of a blast furnace can be repaired during the campaign. 2 areas are consumable and get changed on a cycle measured in months. The stack and bash can be sprayed with refractory material through access points. Extra cooling can be retrofitted into a problem zone. Grout can be injected between shell and lining, but the hearth bottom cannot be repaired without a full reline. The single component whose erosion ends the campaign is the one component that cannot be touched while the furnace is alive. So the entire practice of blast furnace operation is built around delaying one unmeasurable process in one unreachable place using indirect evidence for 2 decades. And the greatest accelerator of that process is not running the furnace hard, it is stopping it, which raises the obvious question. If stopping is so damaging, how does the furnace get the 1,200-degree air it needs to keep burning? And what happens to the enormous volume of gas coming out the top? A blast furnace has to breathe on a scale that is difficult to picture. A mid-sized furnace producing around 140 tons of hot metal an hour consumes something like 180,000 normal cubic meters of hot blast every hour, and that air has to arrive at roughly 1,200 degrees Celsius. Air does not come out of the atmosphere at 1,200 degrees. Something has to heat it continuously forever, and the amount of energy involved is enormous, hundreds of gigajoules per hour, just to raise the air to temperature. The devices that do it are called stoves, and they are worth a moment because they are the most elegant piece of 19th century engineering still in daily industrial use. A stove is a tall steel vessel packed with a lattice of refractory brick called checkerwork. It works in 2 alternating phases. In the first phase, hot gas is burned inside it, and the flue gas passes through the brickwork, dumping heat into the lattice until the bricks are glowing. Then the stove is switched over and cold air from the blowers is pushed through that same brickwork in the other direction, picking the heat back up on its way to the furnace. The bricks are a thermal battery. A plant runs 3 or 4 stoves in rotation, some on gas and some on blast. So the furnace never sees an interruption in its air supply. Both halves of that arrangement are 19th century inventions, and the story of the first one is a small lesson in how confidently an industry can be wrong. Until the 1820s, British iron masters were certain that cold air was better for smelting. It was obvious to them, cold air is denser, so it carries more oxygen, so it must burn better. In 1828, a Scot named James Beaumont Nielsen, who was not an iron master at all but a foreman at the Glasgow gasworks, patented the opposite. He heated the incoming air to about 300 degrees Fahrenheit and watched coal consumption fall from roughly 8 tons per ton of iron to about 5. Higher temperatures saved more still. The established industry fought him, and he spent years in court defending the patent, and within a decade Scotland was the cheapest place in Britain to make iron. The second invention solved the problem Nielsen's version created. His early heating vessels were made of iron, and iron pipes being heated and cooled repeatedly cracked and failed. The same thermal cycling problem 3 generations earlier in a different component. The answer came from Edward Alfred Cowper, who patented a regenerative firebrick stove in 1857 and kept improving it for the next 30 years. Instead of heating metal, heat the brick. Brick tolerates the cycling that iron will not, and the stove that carries his name is still, in principle, the device standing next to every blast furnace in the world today. Some of the Victorian ones were built as tall as the furnaces they served. Now, what is the hot gas being burned in the stoves? This the part that closes the loop. It is the furnace's own exhaust. The gas leaving the top of a blast furnace is not waste. It is a low-calorific fuel gas rich in carbon monoxide produced by the reduction reactions inside the column. It is cleaned and then it is burned in the stoves to heat the blast that goes back into the furnace to produce more of the same gas. The furnace generates the fuel that heats the air that keeps the furnace generating the fuel. Sit with that for a second because it is the same trap the ship's engine sits in, arrived at by a completely different route. While the loop is turning, the blast is nearly free. The energy comes from the process itself. The moment the loop stops, it stops in both directions at once. No blast means no combustion. No combustion means no top gas. No top gas means nothing to fire the stoves. And cold stoves mean no hot blast. A running blast furnace heats itself. A stopped blast furnace cannot restart itself with its own resources because the resource it uses is the running and the steel in the frame of the car you drive, and the beam holding up the building you are sitting in almost certainly came out of a furnace that was already burning before you bought either of them and kept burning for years after. Not a furnace like it. That furnace, the continuity is not a detail of the process. It is the process. There is a second thing the top gas does, and it is the quiet one. The gas leaving the furnaces under pressure, and on most modern plants, that pressure is not simply thrown away either. It is run through a turbine to recover power on the way out. So the same stream of gas is a fuel, a pressure source, and a diagnostic. Its temperature and composition are among the strongest signals operators have about what is happening inside a vessel they cannot see into, which is all very stable, until the day it is not, because roughly 5 times a year, somewhere in the world, one of these furnaces loses its heat anyway. Let us be honest about failure because pretending it does not happen would be absurd. Of the 600 or so blast furnaces operating worldwide, about 5 per year suffer a chilled hearth. It is rare enough that the recovery expertise is concentrated in a handful of firms. One of them has been involved in more than 50 recoveries over several decades, which tells you both how uncommon and how survivable this is. First, the distinction that matters. There are 3 different ways a blast furnace stops, and only one of them is a disaster. The first is a blowdown, which is the planned end of a campaign. The burden is deliberately worked down, the furnace is emptied in a controlled sequence, and it is taken cold on purpose because it is going to be rebuilt anyway. The second is banking. And banking is the interesting one. Banking is a prepared stop designed so the furnace can be restarted quickly and cleanly. Before the blast is taken off, the furnace is charged with a special banking burden carrying extra coke, so there is stored fuel and stored heat sitting in the column while it waits. Then, and this is the part that sounds almost domestic, the furnace is insulated and sealed to keep out 2 specific things, air and water. Air, because any air leaking in will burn the banking coke, spending the heat that was meant to be saved for the restart. Water, because any water leaking in cools the material directly. If either gets in during the bank, the furnace does not simply wait less comfortably. It comes back chilled. Which brings us to the third way, the one that is not planned at all. The dominant cause of a chilled hearth is not a component failing, it is a long, unprepared stop operating irregularities, an equipment breakdown that takes the blast off with no warning, a water leak that was not caught in time, a burden problem that was misread, and then the temperature in the lower furnace falls. The hot metal and slag become viscous, drainage through the tap hole slows and then stops. The connection between the 2 airs and the tap hole is lost, and the furnace has taken the first of the 3 steps. If there is still heat in the hearth, that is a minor chill and it can be worked back. If the temperature keeps falling, the iron itself starts to solidify and that is a severe chill. And in the worst case, everything liquid in the hearth freezes into a single solid mass, several hundred tons of iron and slag fused together against the refractory. That mass has a name. It is called a salamander, and the name has been in the trade for over a century. Recovering from that is not a matter of relighting anything because there is nothing to relight. The classical approach is slow, and if it fails, it leaves the furnace in worse condition than when it started. The modern method is to go in through the tap hole with a refractory protected lance and inject oxygen and fuel gas directly into the hearth. The coke still sitting in there reacts with the oxygen and generates enough local heat to melt the frozen metal from the inside out. It works, and specialist teams have done it dozens of times. It also takes days and sometimes weeks of continuous work to bring a furnace from frozen back to normal production. And if the salamander cannot be melted, it has to be tapped, cut out through the side of the hearth or at an upward angle from below, which means opening the vessel at its structurally most critical point. It is worth being clear about what a recovery actually looks like, because the phrase makes it sound like a repair. It is not. It is a continuous operation running day and night with a specialist team working alongside the plant's own operators, taking a machine that has gone solid and coaxing it back into being liquid without cracking the lining that is left. Every step is a judgment about heat. Too little, and the melt does not propagate; too much in one place, and you damage the hearth you are trying to save. The classical methods are slower and carry a specific trap. If a slow recovery fails, the furnace is left colder and harder to save than when the attempt began, which is why the specialists were built around a faster method in the first place. And the count is the thing that puts it in perspective. Around 5 chilled hearths a year across 600 furnaces. That is a failure rate under 1% annually on a machine holding hundreds of tons of liquid metal at 1500 degrees in a process with no off switch, run continuously for 2 decades. By any reasonable standard, that is an extraordinary record. It is also small enough that almost nobody working at a given plant will have seen one. Now the objection a knowledgeable viewer will raise, and it is a fair one. Furnaces do get stopped routinely for short periods. A brief off blast to change a 2-year or deal with a problem is normal work and does not chill anything because the thermal mass involved is so enormous that a few hours of stillness barely moves the hearth temperature. That is exactly the point. The furnace is protected by its own inertia. Hundreds of tons of liquid metal and thousands of tons of hot refractory do not cool quickly. The danger is not the short stop. It is the long one, and specifically the long one nobody prepared for, which leaves one question. If the machine is this well defended, why do 5 of them a year still go cold? Let us close the 3 stages, because by now every one of them has an answer. The connection between tuyere and tapao is held open by continuous flow, which is held by continuous combustion, which is held by the hot blast, which is held by the stoves, which are heated by the furnace's own top gas. The iron is kept liquid by the enormous thermal inertia of the hearth and by the skull that the cooling system grows on the inside of the wall. And the hearth is kept from freezing solid by every one of those systems working at once, plus a monitoring regime reading 200 thermal zones and thousands of parameters to catch a problem 3 weeks before it becomes a shutdown. That is the whole architecture, and it is remarkable. It also does not include the part that actually decides the outcome. Because a chilled hearth is almost never caused by the failure of any of those systems, it is caused by a stop that was not prepared. Someone has to decide, correctly and in time, that this stop is going to be long enough to need a banking burden. Someone has to seal the furnace properly against air and water and check that the seal held. Someone has to notice that a differential pressure reading on one cooling circuit out of 30 has drifted and treated as urgent rather than logging it. Someone has to read a falling hot metal temperature as the start of the first stage rather than as normal variation, while the furnace is still recoverable. The documented causes are operating irregularities, improper charging, unprepared stops and leaks that ran too long, which is to say the 20-year campaign, the 200 million euro lining, the copper staves, the stoves, the closed gas loop. All of it is load-bearing on judgment. The most sophisticated part of a blast furnace is not in the furnace. And that is also why nobody switches one off. It is not that the fuel is cheap or that demand never drops. It is that the running state is the safe state. A furnace at full blast is protected by its own heat, its own armor, and its own exhaust. A furnace standing still has none of that, and every hour it stands is an hour when the 3 stages are closer than they were. The plant is not paying to keep the furnace burning. It is paying not to find out what the alternative costs. So the next time you pass a steelworks at night and see that dull orange glow over the stacks, you are not looking at a shift that happens to be working late. You are looking at something that has not been dark since long before you drove past it for the first time, and that will not be dark again until a crew arrives with 7,000 of brick to a new one inside the old one. 20 years of continuous fire, held there because stopping costs more than burning, and held there in the end by people who have to keep reading a temperature they cannot see. If this changed the way you look at something you have driven past 100 times, subscribe. This channel opens up the machines that run underneath ordinary life. Next time, the glass furnace, where the material never solidifies and a single power failure can turn the entire tank into a solid block. And tell me in the comments what you think is the real safeguard here, the engineering, or the operator who has to notice in time.